we'll hold that off for later. Thanks for coming tonight.
Okay, so my name is Craig Brown. I'll be talking about some NoSQL databases. We're going to try and give you kind of a high-level overview, more of an intro, cover some of the specifics about some of the products, compare kind of the RDBMS or SQL databases that we all know and want to use every day. So my goal is to kind of give a bit of an education here. I'll probably generate a lot more questions than I'm going to give the answers, but I think that's a good thing. It'll be good to kind of think about how this relates to maybe some of the work you're doing, particularly the data model that you have, and the particular programming problems you have. So a little bit about myself here. I work currently for a company called Yahoo.com. It's a genealogy startup. A lot of you have known me actually from Overstock, left Overstock a couple months ago. Excellent place to work, a lot of great people there, appreciate it a lot. So I have a blog that's up here that I have a lot more information on. You're welcome to go there and you know, check out some of the information I have and that's for you as well. So a little bit of the agenda here. We're going to kind of cover what is NoSQL and what's general, what's not. An overview of the landscape, some of the vocabulary, a little bit about the CAP theorem. Some of you may be familiar about that. It kind of governs how your data is kind of stored or replicated. A little bit of comparison between SQL and NoSQL data stores to try and take you from the kind of stuff that we know to the place that we don't know just yet. And then we're going to go through an overview of each type, a little bit of detail about what makes these different products unique and desirable. And we'll go through some questions. So NoSQL does not mean NoSQL. Actually, it has very little to do with SQL in general. NoSQL is supposed to mean not only SQL, so it's one of those kind of unfortunate acronyms that we have up here. The truth of the matter is they actually work really well here. Most companies do not, bring in a NoSQL data store and completely do away with all the SQL or RDBMSs. They're going to use their RDBMSs for what they're strong at. They're going to use a specific NoSQL data store to solve some particular problem that the value will solve, or not solve as well with RDBMS. So this is a little bit of a breakdown. On your left-hand side here, I'm putting what I call row stores. This isn't completely fair what I lumped here together, but this isn't the group that I'm necessarily concerned about talking about. But these are generally considered row stores because of the way they store the information on disk. Object relational is going to be slightly different there. On your right here, we have, starting at the top, we have our column store database, which refers to how the data is kind of stored and accessed. And then next we've got a document of key value stores. These are basically really big hashes. We're all used to dealing with hashes. The next one is a memory store. Memory stores and document stores are really similar in their data model, essentially the same, but their scalability model, their storage models tend to be quite a bit different. And the purpose, the reason why people are using these, this is one of the reasons why I separated these. A lot of times you'll see them, these two kind of put together because of their data models being so similar. And the last one being graph or triple stores have to do with storing relationship kind of information. Bill knows Joe. You can specify how strong that relationship is. And what is bidirectional? Maybe Bill doesn't like it. Bill doesn't like it. So a little bit of history. In the black here is our SQL databases. In the blue, we've got the NoSQL data stores. As you can see, there's a lot of recent developments, especially in the last 5 to 10 years in the SQL space. A lot of these new data stores are coming up, and a lot of companies are developing these to solve very specific problems. And we see that when we talk a little bit about some of the individual categories. So a little bit about the vocabulary here, some of the things we're going to be talking about. So we have a CAP theorem, which has to do with consistency, availability, consistency, availability, and partitioning. We usually have my screen here. My screen is blank at the moment. I apologize. I have to keep looking out there to make sure. So ACID commits, This is all the stuff that we really love with our RDB messages when we make any kind of commit, we know it's committed, we have guarantees on that. The polar opposite of that is called base transaction. So basically available, soft state, and eventually consistent. So those are probably going to be some new terms, but we'll talk about that a little bit more. It just has to do with how it stores and manipulates the data, especially in a distributed environment. RDF is an important one, the resource description framework. Has to do with the W3C committee on the semantic layer. So in other words, trying to bring meaning to all the information that we have out there. That has to do very much with your graph, the purpose for that point. Sharding, it's just a little bit of a term for partitioning and distributing your data. And then the last one, web scale, is a term that generally means really big, right? Hundreds of millions or billions of rows of information, thousands of servers and clusters, the Googles, the Twitters, the Facebooks, are really huge things. These companies are doing things that almost no other company in the world is doing. In a lot of cases, they have developed specific tools to be able to do it as well. So this is our CAP diagram. So CAP theorem basically states that you can have consistency, availability, or partition tolerance, but not all three at the same time. So we've got a deal link here. As developers and engineers are used to trading. It's like, yeah, I can get you that in a month, but I can't get you those features. You want those features, it's going to take 6 months, right? So consistency has to do with your clients and what view of the data that they get. If client A makes an update, what does client B see and how soon do they see that? Availability and partition tolerance are kind of two sides of the same coin, and they have to do with availability has to do with losing nodes, and partition tolerance has to do with basically your network tolerance. And so availability would look like, for example, if you lose a node, maybe your cluster is not available for reads, or your cluster is not available for writes, depending on what the situation is. So if you have a master-slave scenario where you lose your master, which is a node, your data store may not be available for writes, but may be available for reads. Partition tolerance has to do with losing sections of the network. So if you have a switch that goes down, but your nodes are still available, what happens to the rest of the nodes? Can they communicate, or when the communication is restored, does the network be able, or does your cluster be able to recover and do that? So normally what we live in is consistency and availability, and not necessarily partitioning. So that's a single node system. As soon as you add partitioning, as soon as you're dividing your data up over multiple nodes, multiple systems, then you've got some trade-offs to make. And a lot of times the trade-offs are made in consistency, but it depends on what the application is. So some of the parameters that go into tuning CAP, you have N, which is your number of copies that you make, your number of replicas of your data. R has to do with your read core, and write has to do with your write core, W1. So that's how many copies have to agree before you're going to consider that transaction successful, right? So for example, if you're keeping 3 copies of your data over your whole cluster, you can specify hard consistency, which would mean when I do a write, I want to make sure that all 3 copies agree before I consider that write successful. And that may be, very necessary depending on your situation. But it's going to be a little bit slower because you've got to have agreement between these 3 nodes, right? You could also say, well, this data is kind of not terribly important. I can generate it. I want to keep 3 copies, but I only want to make sure at least 1 copy is good. And then the cluster will take care of distributing the rest of those writes. But as soon as it gets 1 good write, it will ignite it down and go on. It's kind of the same thing on reads. If you specify 3 copies and a form of 2 on read, you want to make sure if you read 3 copies, you've got at least 2 good copies before you're going to consider that read successful. So the